Hi, folks. Now we move in Chapter 8, where we will be talking about hypothesis testing. And here in Section 8.2, we will talk about the basic ideas behind hypothesis testing. And then in the future sections of Chapter 8, we'll talk about how to do hypothesis testing for these different population parameters. So in this section, we will be talking about the sequence of steps that go into doing hypothesis testing. Excuse me, I'm talking a little bit funny because I have a sore on my tongue, so bear with me, please. We'll talk about how to express a null hypothesis and an alternative hypothesis from a given claim, and how to express both in symbolic form, in the form of either an equation or an inequality. We'll talk about how to calculate the value of a test statistic given a claim and some sample data. Well, we'll talk about how to choose a sampling distribution that is relevant. We'll talk about how to calculate a p-value as one of two methodologies in deciding whether to reject the null hypothesis or not. Otherwise, we can use the critical value. I'll show you how to both use and calculate the p-value and the critical value. But you can use one or the other. But you get the same results anyway. And then we'll talk about how to state the conclusion from your hypothesis test about a claim that is simple and non-technical. Now, what is a hypothesis? A hypothesis is a claim or a statement about a property of a population. It could be as simple as saying that I have a fair coin, a coin that is equally balanced, or that I have a fair die, that each side is equally likely to come up. Or I could say that I have a method that increases the likelihood of, of getting, when a couple tries to conceive, of getting one sex or the other. A hypothesis test is a procedure for testing that claim. And very particularly is testing a claim about a property of a population, in which we are making a claim about, some population, whether it's, coin flips or siblings, within a group of children, or bushels of hay, or whatever. And we're going to test that claim by using a sequence of steps. So we're going to be learning about hypothesis testing here in Chapter 8. Now we are going to reiterate something that we've talked about before, in that if we make an assumption, and under that assumption it's very unlikely for some event to happen, then that means that assumption that we made is probably not true. So for example, suppose that I pull a quarter out of my pocket and I'm going to assume that it's a fair coin. But then I flip the coin, say 1,000 times, and it turns out that I came up with 992 heads out of 1,000 coin flips. Now, the probability of that sort of thing happening is very small. The probability of getting at least 992 heads out of 1,000 coin flips is very small. Now, it could be possible for us to have a fair coin and to have flipped 992 heads, but the more likely explanation is that the coin was not a fair coin, but it was weighted. Okay? Now we're going to use that idea regarding this rare event rule for inferential statistics in the hypothesis test. Okay? Now, we mentioned earlier a null hypothesis. Well, it's a hypothesis in which, we're going to make a claim in the form of an equality about some population parameter. Mu, proportion, sigma squared, in the form of an equality. We're going to say that mu is equal to 3, or sigma is equal to 13.2, or proportion P is equal to 0.5, or whatever. It's in the form of an equation. We're going to test the null hypothesis directly in the sense that we assume it is true and reach a conclusion and calculate the probability of getting that result as extreme as it was. And based on that probability, we will either reject or fail to reject that null hypothesis. The alternative hypothesis will be a secondary claim in the form of an inequality, less than, greater than, or not equal to sort of statement that says that the parameter is not equal to, less than, or greater than some number. We use this notation H sub 1 or H sub A for our alternative hypothesis, as distinguished by or compared to the null hypothesis, which is denoted by H sub 0. Now, if you are conducting a study and you want to use a hypothesis test to support your claim, the claim must be worded so that it becomes the alternative hypothesis. Okay? Now, our claim is typically in the form of an at least, or greater than, less than, not equal to, that sort of thing. So typically our statement that we're making for our claim is going to actually go into our alternative hypothesis. So we are going to state two hypotheses. One is going to be in the form of an equation. That's going to be H sub 0. That's our null hypothesis. And H sub 1 will be in the form of a greater than, less than, or not equal to sort of inequality. So for example, and this is the same example that we're going to deal with this entire section. Suppose that we have a business owner who's come up with this product or this procedure to help couples who are trying to conceive and they want a girl. And this method is supposed to increase the likelihood that they conceive a girl. Now, to test the claim that this product is more likely to result in a girl being conceived, we're going to go ahead and take a sample of 100 babies born from this method. Okay. Now, to start off with, before we get any further, let's think about our hypotheses. We're going to test the claim that the proportion of babies born as girls is going to be greater than 0.5. Why do we say it this way? Well, if the method was not effective, then there would be equally likelihood of a boy versus a girl. So that means that approximately 50% of the babies would be girls and 50% of the babies would be boys. Just like a coin flip. Suppose I have a coin. So it could be fair, in which case the proportion of heads that come up is 50%. But if I have a notion that it's weighted towards heads, I could have an alternative to say that the proportion coin flips resulting in heads would be greater than 50%. Okay. Moving along here. Then we would state a level of significance, which we give as the letter alpha, alpha, Greek letter alpha. Typically, alpha is going to be set at 0.05, some small decimal. Could be as small as 0.01. In fact, 0.05, 0.01 are the two most common levels. But theoretically, alpha could be any decimal between 0 and 1. Very rare for it to be greater than 0.1. In fact, it wouldn't make sense. But most of the time it's going to be 0.05, as you shall see. We call alpha the significance level. We also recognize the significance level alpha as the probability that the test statistic will fall in the critical region when the null hypothesis is actually true, aka making the mistake of rejecting the null hypothesis when it's actually true. Okay? Now, regarding your test statistic, if we're testing the claim regarding the population proportion P, we will use the normal distribution as an approximation to the binomial distribution. And if you remember back from that section in Chapter 7 where I think it was Chapter 7, or Chapter 6, I forget, where we were doing the normal approximation of the binomial, well, this is the statistic that we calculated here, where we take p hat minus p. Now, p hat is your sample proportion, p is your hypothesized population proportion from the null hypothesis, divided by the square root of pq over n, where q is 1 minus p, and n is the sample size. As we'll see in section 8.4, when we want to test a claim about the population mean mu, we'll either use the t or the z distribution. We'll use t if we do not know the population standard deviation, or we'll use the z distribution like you see here on the right when we do know, or at least can make an assumption of the population standard deviation sigma. If we're going to test a claim regarding the population standard deviation sigma or the variance sigma squared, then we will use the chi-square distribution with this calculation right here, n minus 1 times s squared over sigma squared. All of these test statistics, we have to make sure that we verify the requirements. Just to reiterate what a test statistic is, it is a value used in making a decision about the null hypothesis, and is found by converting the sample statistic to a score with the assumption that the null hypothesis is true. Step 6, after we had computed the test statistic value, we will either compute a p-value or a critical value. And I will show you how to do both. Now, let's go back to our example with the XOR method. Alright, we're going to calculate p hat, and we're going to calculate our test statistic, going through the various steps here. Okay, so first step, null hypothesis, the population proportion, as in the proportion of babies born that are girls, is 0.5. That's another way of saying that the method was ineffective. And if we don't think that's true, if we have enough evidence to reject that, then we would accept or conclude, not accept, but conclude that the alternative is true, which tells us that p is greater than 0.5. Because of the fact that we are testing this claim that this XOR method of gender selection increases the likelihood of having a baby girl. Now we're going to work under the assumption that the null hypothesis is true with p is equal to 0.5. Remember, alpha is going to be 0.05. Sample proportion of 58 girls was observed in our sample in 100 births, not 10, by the way, sorry. 58 out of 100 births result in p hat of 0.58. You just take the number of successes divided by the sample size to get a decimal. 0.58 in this case is p hat. Now, compare p hat to the hypothesized value of p. 0.58 versus 0.5. Now the question is 0.58 really all that far from 0.5? Is the observed proportion significantly far away from the null hypothesized value for p? Well, we shall find out. Now, here's the statistic that we're going to use. Again, this comes from the normal approximation to the binomial distribution. So z, as in the standard normal distribution, is going to be p hat minus p over the square root of pq over n. You plug in the 0.58 p hat statistic that we calculated, and then everywhere you see p, that is from the null hypothesis. Plug in 0.5. And then 1 minus 0.5 is q, and that's 0.5, over the sample size of 100 n. So how this calculation goes is you're going to take 0.5 times 0.5 divided by 100, take the square root of that, and then 0.58 minus 0.5, which is 0.08, by the way, divided by that square root. And that's going to be equal to 1.60. Now, the question is 1.60 all that uncommon? Well, as we shall see, it's really not going to be that one common, because our result is 1.60 standard deviations from the mean. Anything outside of 2 standard deviations away from what was expected would be unusual. In fact, the real thing would be about 1.96, except this is a one-tailed test, as we shall see. But still, that is not that far away from the mean. Now, when I talked about a two-tailed test, that comes from the sort of alternative hypothesis that we have, if it was not equal to. Otherwise, if we had a one-tailed test, that corresponds to your alternative hypothesis being a less than or greater than sort of inequality. The tails that we're talking about in this distribution are the extreme regions bounded by critical values. So it's important for us to know whether we have one tail or two tails, because as we can read here, determinations of p-values and critical values are affected by whether a critical region is in two tails, or the left tail, or the right tail. Therefore, it becomes important to correctly characterize a hypothesis test as two-tailed, left-tailed, or right-tailed. Now, for the two-tailed test, we're going to take alpha and divide it in half and put half of alpha in each of the two tails. Now, again, what we mean by the tails is the extreme parts of the distribution far away from the mean. For the two-tailed test, we have both tails under consideration. What we do is we look for those critical values that separate this region with area under the curve of alpha over 2 to the left and to the right. For the z distribution, we use symmetry to help us out with that. Otherwise, when we use the p-value method, we calculate the probability that we could have gotten a test statistic value at least as extreme as we did in the one direction, and then we multiply by 2, as we shall see. But when we have a left-tailed test, that corresponds to our alternative hypothesis being a less than sort of inequality. And the direction of the inequality gives the direction of the tail. A less than sort of inequality corresponds to a left-tailed test. A right-tailed test corresponds with a greater than sort of inequality for the alternative hypothesis. And again, for the right-tailed test and the left-tailed test, all of alpha is in the tail. Whereas for the two-tailed test, alpha over 2, half of alpha is in each of the two tails. But for the one-tailed test, all of alpha is in the one tail. What exactly is the p-value? If we choose to use the p-value to help us decide whether to reject or not reject the null hypothesis, the p-value is one methodology. The critical value is the other methodology. We'll talk about critical values later. P-value, also known as the probability value, but almost nobody talks about it as the probability value. We just call it the p-value with a capital P. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. If our critical region is in the left tail, then our p-value is area to the left of the test statistic under the curve. And likewise, for the critical region being in the right tail, the p-value is the area to the right of the test statistic under the curve. And then the critical region, if you have a two-tailed test, that means you have critical region two tails. And the p-value is twice the area in the tail that is beyond the test statistic relative to the mean. So out beyond, going outwards. So it's twice the area in the tail beyond the test statistic. You compare your p-value against your alpha value, typically 0.05. And if your p-value is less than or equal to alpha, you would reject the null hypothesis. So continuing with our example with the XOR method, here's our null and alternative hypothesis that we're familiar with now. Here's your test statistic. We calculated it as 1.60. Now, this is a one-tailed test. It's a right-tailed test because of the alternative hypothesis being a greater than sort of inequality. So we need to find the area under the curve to the right of 1.60. Now, I'm going to show you how to look that up. In fact, you already know how to look it up, but I'm going to do it anyway. Show you anyway. All right, hold on here. Sorry, having a little minor difficulty there. Had to restart the computer a bunch of times today because of updates being applied. So I'm going to pull out my Z table. There's my Z table. All right. Now, 1.60, we want to find the area to the right, but the Z table gives us area to the left. So by symmetry, I will find the area to the left of negative 1.60 and then that'll be the same area to the right of positive 1.60. Negative 1.60, here's negative 1.6, and then 0. And that area is 0.058 right there. 0.058. So going back to our slideshow here, there's our p-value. And notice, by the way, that it's greater than 0.05, greater than alpha, knowing that is going to be important. This little chart gives you instructions on calculating your p-value. It starts off up here, doing your hypothesis testing. Now, are you doing a left-tailed test, right-tailed test, or a two-tailed test? If you're doing a left-tailed test, then your p-value is going to be the area to the left of the test statistic. If you're doing a right-tailed test, your p-value is the area to the right of the test statistic. If you're doing a two-tailed test, and if your test statistic is to the left of center, then your p-value is going to be twice the area to the left of the test statistic. Excuse me. Otherwise, if the test statistic is to the right of center, then your p-value is going to be twice the area to the right of the test statistic. Now, you heard us talk about critical region earlier. What exactly is the critical region? Well, that's going to be that area under the curve that corresponds to all the possible values of your test statistic, which would cause us to reject the null hypothesis. Because the probability of getting that test statistic value, at least as extreme as it is going to be less than alpha. So, that critical value is kind of a marker that demarcates that region under the curve between that region in which we do not reject the null hypothesis and we do reject the null hypothesis. Critical values depend on the nature of the null hypothesis, sampling distribution that applies, and the significance level alpha. Going back to our example here. Now, the critical region is going to be that area or that region under the curve that has an area of alpha. Now, this is a right-tailed test, so what we need to do to find this critical value, which basically gives that demarcation between the so-called critical region in red and the non-critical region to the left in green, to find the z value, we need to do this. Here's the thinking. If the area under the curve in the red, in the critical region, is equal to 0.05, then that means the area to the left of this critical value is 0.95, because the total area under the curve is 1. So the critical value is at the 95th percentile. Now, we could use symmetry as well, though. So I'm going to show you two different ways to find this critical value. First of all, I'm going to use symmetry, because if I'm going to find that z-score associated with 0.05 area under the curve to the left, and then take the positive of it. Otherwise, I could look up that z-value corresponding to the 95th percentile. All right, let's go to our z table. Hold on here. There's our z table. Now, let's do that first part first. Now, let's find the z-score corresponding to 0.05 area under the curve to the left. and it's going to be about halfway between here and here. Finding that probability, that area under the curve that, matches any of these numbers. The number in the table that's closest to 0.05 is either this one or this one. And the corresponding z-score is negative 1.6, either negative 1.64 or negative 1.65. Okay, so we could either choose negative 1.64, negative 1.65, or go halfway between. Because after all, 0.05 is exactly halfway between these two guys right here. Otherwise, we can go with negative 1.645. And the positive of that is 1.645, because there will be an area of 0.05 to the right of it by symmetry. So that's one way of getting the 1.645 here. The other way that I could think of using the table is going to the second page and looking up 0.95 area to the left under the curve, because after all, that's what Z table does. It gives you area under the curve to the left. So look for 0.95. Well, there's no 0.95, but there's 0.9495 and the 0.9505. 0.950 will be halfway between these two guys. And the z-scores under consideration will be 1.64, 1.65. Halfway in between will give us a z-score of 1.645. Okay? So that's the second way that we get 1.645 as our critical value. Now I'm going to remind you, and I'll say this again a few more times too, is that when you're doing your hypothesis testing, you could use either the p-value test methodology or the critical value methodology. It really doesn't matter, because they'll both result in the same conclusion. So I've already shown you how to use p-value and also how to do the critical value. For the critical value here, notice that our test statistic, which was 1.60, remember where the 1.60 comes from? It was from this calculation here. Our test statistic was 1.60. Notice that our test statistic value does not take us into the critical zone or critical region, otherwise known as the rejection region or rejection zone. When your test statistic is at least as extreme as your critical value, you would reject the null hypothesis. In this case, that's not the case. Our test statistic is not as extreme as your critical value. So we would fail to reject the null hypothesis. By the way, don't confuse p-value with the proportion p. P is a population parameter, whereas the p-value is the probability of getting a test statistic that's at least as extreme as the one representing sample data. Then the next step is to make a decision. Do we reject or not reject the null hypothesis? I think I've hinted at it, that, it depends on if you use the p-value or the critical value. But actually it doesn't depend. You're going to have the same outcome. For your p-value method, if your p-value is less than or equal to alpha, you would reject the null hypothesis. If your p-value is greater than alpha, you would fail to reject the null hypothesis. In our case, our p-value is greater than 0.05. So we would fail to reject. Now, critical value method, if our test statistic was at least as extreme as the critical value, we would reject. But in our case, it wasn't. our test statistic fell short of that critical value. So we, again, failed to reject. I'm going to say it one more time. If you use one method, the critical value method, that will give you the same result as your p-value method, and vice versa. So going back to our example here, here's our null hypothesis, alternative hypothesis, test statistic, 1.60. We calculated a p-value, 0.0548. That's greater than 0.05, so we failed to reject the null hypothesis. Or you could say that the critical value was 1.645, our test statistics was 1.60, not as extreme. We failed to reject the null hypothesis. Come to the same conclusion either way. So then how do we state our conclusion? Well, you're going to want to state it in a way that an average Joe, an average person can understand, so it's not technical. Now, our null hypothesis in this problem was that P was equal to 0.5. What does that mean? That basically means that the proportion of babies born to families who use this method, that the proportion of babies born was going to be, or that were girls, is going to be equal to 0.5, which is another way of saying that the method is ineffective. That was what our null hypothesis was. But we could say that we failed to reject the null hypothesis that P is equal to 0.5, but what does that mean? That means that we have no reason to believe that the method is effective, because we failed to reject the null hypothesis that the method was ineffective. Okay? So make sure that you state your conclusion in a way that the average person can understand. So we don't have enough method to reject the null hypothesis. So that's another way of saying that there's not enough sufficient evidence to support the claim that this XOR method is effective in increasing the probability that baby girl will be born. Now, if it turned out that we did reject the null hypothesis, that means that we would conclude that P was greater than 0.5. In which case we would say that there is sufficient evidence to conclude that the method is effective. And this little flow chart, I'll let you read it on your own, but this basically gives you some guidance on how to state the wording of your conclusion based on how you are testing your claim. Does the original claim contain an inequality or an inequality? If it contains an inequality, and that means that will be a null hypothesis. But if it was an inequality, then it became an alternative hypothesis. So anyway, go ahead and follow the flow chart to see how you would state the wording of your conclusion. Now, here's a caution for us to observe here. When we state our conclusion for hypothesis test, we're either going to say that we reject or fail to reject the null hypothesis, and therefore there is enough evidence to support the claim, or no, whatever. But we don't say that we accept a null hypothesis, or that we accept an alternative. We don't say that. We don't use the word accept. We either reject or we fail to object or reject. We either reject or we fail to reject the null hypothesis. If we fail to reject the null hypothesis, we would conclude that the null hypothesis is true because we don't have enough evidence to reject it. Okay? Now, it could be that we make a mistake. Maybe our sample was not very representative of the population, in which case it's entirely possible for us to come to the wrong conclusion. We could either reject a null hypothesis that in reality turns out to be true, in which case we would be committing a type 1 error. Which, by the way, alpha, which is our level of significance, is also the same probability as committing a type 1 error. Or we can commit a type 2 error, in which case we fail to reject a null hypothesis that in reality is false. The probability of making a type 2 error is called beta, Greek letter beta. Again, it's just a probability, typically small, 0.05, 0.10, that sort of thing. This little table kind of gives us a little bit of a way of organizing the errors here. Type 1 error is where we reject the null hypothesis, but it's true. But if we reject the null hypothesis and the null hypothesis is false, then we made the correct decision. If we fail to reject the null hypothesis and the hypothesis is true, then we made the correct decision. Finally, if we fail to reject the null hypothesis, but the null hypothesis is false, then we've committed a type 2 error. So as it applies to our example here, a type 1 error would be if we rejected a null hypothesis that's actually true. Now, for our example, the null hypothesis was that the method was ineffective. So if we rejected it, then we would conclude that it was effective, when in reality it was not effective. That would be the type 1 error. The type 2 error would be if we fail to reject the null hypothesis and conclude that it is ineffective, and when in reality the method was effective. Okay? Now, we would like to minimize the probability of making any sort of mistakes. So we want to kind of keep alpha and beta as small as possible. The problem is that you can't simultaneously make alpha and beta small without increasing sample size. Okay, if you have a fixed sample size and you increase alpha, then you decrease beta, and vice versa. All right. Now, in a more advanced math class, you'll talk about how to calculate beta, but it depends on sample size partly. You talk a little bit about power of a test, and I'm just going to mention this in passing because it's not a big topic here. But what a power of a hypothesis test is, it's the probability 1 minus beta. And it's the probability of detecting a difference between what you should have gotten and what you actually got. Let's go ahead and read through this. The value of the power is computed by using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed true in the null hypothesis. And just as 0.05 is a common choice for a significance level alpha, a power of at least 0.8 is a common requirement for determining that a hypothesis test is effective. You could go a little bit higher if you need to, but that comes at a cost. When designing an experiment, we might consider how much of a difference between the claimed value of a parameter and its true value is an important amount of difference. When designing an experiment, a goal of having a power value of at least 0.8 can often be used to determine the minimum required sample size. So yes, you can state what power level that you want, and then from there compute a sample size that way. Again, you're not going to worry about that in this course. Okay, so with that, we are done talking about the basic ideas behind hypothesis testing. I'm going to try to record at least one more video this evening before I take off on my trip, okay? Well, you folks have a good day, and we'll see you next time.